All right, so we're going to continue on with collisions. I know I wasn't there with you last day out, but there was a couple of days there dealing with momentum and the conservation of momentum, which sometimes happens with collisions, or in a case of maybe a cannonball or a gun shooting something, where you have zero momentum initially, say with a gun and a bullet, because nothing's moving, even though you do have mass. Afterwards, the bullet obviously is moving very quickly, and the gun has a kick fire. And again, looking at the conservation of momentum, which again is going to be involved with today, big time, because we're doing collisions. All right, now we're going to look at two, I guess, basic types of collisions. There's really kind of three, but there's one within one. And the first one we're going to look at is what's called elastic collisions. So in all of these collisions that I'm going to talk about, the key thing is that momentum is always conserved, which means the momentum before, which we have a little funny symbol there. I believe it's a rho, again, a Greek letter. And because it's mass times velocity, it is a vector, is equal to the momentum after. Now, a little bit of a notation change here. Instead of writing before and after, I put a little tick there. And that is prime, which means afterwards. All right. Now that is also a notation that's used in calculus. Totally different meaning though. But again, we have momentum before is equal to the momentum after. Again, after is denoted with a prime symbol. All right. Now, here's the key with our two different types of collisions today. We have what's called an elastic collision. Now, to be honest with you, that's more or less a normal collision. And what I mean by that is that energy is lost in the collision. Momentum is not lost, but energy is lost in some form. For example, a car accident, if two cars smush each other, that is obviously a collision, but some of the energy during that collision, not only is it used to move the cars in different directions, but it's also used to deform the car in terms of work being done where there's a force smashing the car in a little bit, say a fender getting destroyed, or in fact, that's how they design cars, that it absorbs energy, the bumper system, and on both ends. So what happens there is that energy is lost in an elastic collision, and so that your kinetic energy that you had before does not equal your kinetic energy after. That's the key with an elastic collision. Now, something that is kind of like a more of an ideal situation is what we call a inelastic collision. Oh, sorry, I got mixed up. Elastic collision, perfectly elastic. Sorry, kinetic energy is conserved. Inelastic is like our car accident, where things happen where they hit and energy is lost. All right, and now a perfectly inelastic collision, inelastic, nothing's rebounding, is when two cars smash together and then they hook up and they become one object. Now that's a perfectly inelastic collision. Again, with inelastic, they smush together, and so energy is lost. And so the energy we had before does not equal the energy after. Where again, a perfect elastic collision, perfectly elastic, is in where our kinetic energy, because that's what we had, speed before and mass, is equal to the energy afterwards. Again, difference between elastic and inelastic. Elastic, you think of a perfect rebound. Now, I think the closest situation that I could come up with for an elastic collision in the real world is those little balls. You ever see those little balls that go tick, 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 tick? Now, it's not perfectly elastic collision, but I guess that's essentially the reason, or the closest example that I could think of in real life, because generally there's going to be energy lost somewhere along the line. And even with those little balls, energy is lost, but it's very, very small. And that's why those balls can keep going back and forth. I'm not sure what a Newton's cradle is. I'll have to look it up. Maybe that's the same idea, or is that what those balls are called? I'm not sure, because they do kind of go back and forth like a cradle. So how do we apply that? So again, we have two different collisions. Elastic, kinetic energy, no energy is lost. So kinetic energy is what we had before. None of it is lost. But when we have an inelastic, and again, it's in the words, inelastic, you're not having a complete rebound. Kinetic energy is lost. Perfectly inelastic is when they hit together and there's no rebound because they stay together and continue on. Like a car accident when two cars get hooked up together. All right, now, here we go. So collision. So we get to example one. It says a 0.5 kilogram object is moving at a velocity of 5 meters per second east. When it collides head on with a stationary object, 1 kilogram object, All right, now if the 0.5 kilogram object rebounds directly backwards at 1.2 meters per second, was the collision elastic? So is the energy conserved? All right, so here we go, because momentum, again, with collisions, always conserved. Now the difference is in the kinetic energy. All right, so I look at our two masses here, and I have M1, which is 0.5 kilograms. M2, our second mass, was 1 kilogram. Now our V1, the velocity of our initial velocity of our first object here, was 5 meters per second east. All right, now, what we don't know, or do we know? Well, we do know the second velocity. Now, this is where the notation changes, because here's what happens with the notations. I have a V1, well, that's usually our initial velocity, but here we have two objects. So we're gonna have a V1, V2. There's a lot of notation here. So it's second velocity after the collision for object one, I'm gonna call V1, still the velocity of object one, but after the collision. So I have a little prime symbol. And it goes backwards at 1.2 meters per second. So 1.2 meters per second. And if forward is east, backwards is west. All right, now the velocities of my second object. So I have a V2. Now that object initially is at rest. All right, its velocity afterwards, V2 prime. I don't believe we know. We don't know. Okay. Now, if this is an elastic collision, what I have to look at again is the energy before and after. But to find the kinetic energy before and after, I need to know all the velocities and masses. I am missing this velocity. So I need that velocity so that I can look at my kinetic energy before and after. All right, but again, with collisions, momentum is conserved. So again, the momentum we have before, which is going to be M1, V1, there is the momentum of object one initially, plus M2 times V2, that's the momentum of the second object initially, has to be equal to the momentum afterwards. And so what I'm going to have is M1 times V1 prime, because the masses aren't changing, right? The velocities are, plus M2 V2. And again, the idea here is I'm finding V2 prime, because I know this, I know this, I know this, I know this, I know everything else. All right, so I'm going to substitute in here my values. So I got a 0.5 times V1. Now, again, we have direction here. That matters. I always, again, use 95% of the time, I won't say always, I use east as positive, west as negative. All right, so I'm going to have a positive 5 here. All right, plus. Now, my second object wasn't even moving initially. So the momentum is 0. You have to have some speed to have some momentum. All right, now, again, plugging in my values, M1 here is 0.5. V1 prime, it's west, 1.2 west, so I'm going to have a negative 1.2 here. And my mass 2 here is 1, and I am trying to find V2 prime. All right, so I'm going to do a little math here. That's at 0. Half of 5 is 2.5. And then I got a half a negative 0.2. Well, I know it's going to be negative 0.6. Plus a V2 prime, or 1 V2 prime, same thing. I'm going to move this negative 0.6 over to the other side, and that would just be adding then. So I'm going to go 2.5 plus 0.6. That's going to be a 3.1 is equal to V2 prime, which means I can actually say that that's V2 prime is equal to 3.1 meters per second. And again, because it's positive, that means it's in the east direction. All right, so they hit each other, right? If east is to the right, west, V1 hits V2, it goes to the east, and this rebounds back. All right, so now we know my velocity of my second mass after the collision. But again, we're looking at, is this an elastic collision? So I want to look at the kinetic energy before to see if it is equal to the kinetic energy afterwards. All right, so are they equal? I don't know. So let's check it out. Again, the kinetic energy before, so my EK, I'll do this two separate steps or two separate equations here. So again, the kinetic energy before, I'm going to have 1/2 m1 v1 squared. There's a lot of notation there. Plus 1/2 m2 v2 squared. All right, so these are all my velocities and, well, masses initially. All right, so plugging in here, I have 0.5 times m1, which is 0.5, times v1 squared. Again, that's a 5 squared. Now, again, my second object had no velocity initially, so it's got no kinetic energy. All right, and so if I find my kinetic energy there, I take 5 squared, that's 25. Half of that is 12.5. Half of 12.5 is, I believe, 6.25. And again, we're talking about kinetic energy, so that is how much kinetic energy we had initially, 6.25 joules. All right, I need to compare it to what we call, again, notation, EK prime, the kinetic energy after, which again will be now 1/2 m1. Now watch, check out this subscript. v1 prime squared. Lots going on there. That is the velocity of object 1 after the collision. And then I got to square it. All right, plus 1/2 m2 v2 prime squared. Again, the prime means after the collision. All right, so substituting my values here. So let's see. I have a half, that's 0.5. The mass was 0.5. And my velocity after the collision, negative 1.2 squared. All right, plus, running out of room here. I have 0.5 as the half. The mass 2 was 1. And the velocity afterwards, we found that out, 3.1 squared. All right, little badness here. So I got to do the exponents and then the multiplying. All right, so I take negative 1.2 squared times a half, and I end up with 0.36. Plus the other part there, now I got to take 3.1 squared times 1, so that's not going to change nothing, times a half, and I get 4.81. I add these two up, and let's see here, 4.81 plus 30.36, so I end up with 5.17 joules. And so if I'm looking at, is this collision elastic? Does the kinetic energy before equal the kinetic energy after? It doesn't. So EK does not equal EK prime, and therefore the collision is inelastic. So some energy has been lost somehow to deform something, or heat, or sound. Sound is another thing when you have a collision. Sound is energy, so that is part of what's going on there. All right, so there's a big one. Now we get into the second example. A little bit of math coming your way here. No trig, though. No trig. We are going to do a little more grade 10 math. Solving systems of equations is coming here. All right. All right, so we get to our second example. On a frictionless pool table, which is pretty close to frictionless, but it's not, but this one is. The white ball, which is 0.4 kilograms, is shot at the 7 ball, 0.28 kilograms. I believe those values are actually real. At a velocity of 2.3 meters per second. Okay, if the collision is elastic, which again is going to mean that our energy is conserved, our kinetic energy is conserved, determine the velocity of each ball. Not a lot of information here, right? Okay, so here's what we're going to do is we got our objects. So I'm going to go off with M1 first. That's 0.4 kilograms. Now that ball is shot with a velocity of 2.3 meters per second. I guess that's forward. So we'll go V1 is equal to 2.3 meters per second, and I'm going to say forward. All right. Determine the velocity of each ball afterwards. That means I don't know V1 prime. Okay, now what about the other equation here? Or the other mass? We have M2, which is a smaller ball, 0.28 kilograms. All right, V2, the velocity initially, well, if you've ever played some pool, you realize that only one ball gets to move at the start, and that's the white ball. And so V2 is 0. Do I know the velocity afterwards? I do not. So now we have two things unknown. But here's the deal, is we do know that conservation of momentum with collisions, the momentum before is equal to the momentum afterwards. All right, so rho is equal to rho prime. All right, so the other thing I know, so I'm going to get one equation out of this, because again, I said we're going to get down to two equations, two unknowns. The other equation is this is an elastic collision. So when they collide, kinetic energy is conserved. So EK is equal to EK prime. All right, so again, I'm going to substitute in these values. So my initial momentum is we have M1 times V1. So there's 0.4 times my 2.3 plus the momentum of the second object. But since the initial velocity of the second object is 0, we get a 0 there. Now is equal to the momentum afterwards. So we're going to have M1 again, which is 0.4 times V1 prime. Plus, we got the momentum of the second object, which is 0.28 times, what do we got here? V2 prime. We don't know that. All right. So I can simplify this equation. Let's see here. I take 0.4 times 2.3. What do I get here? 0.92 is equal to, let's see here, 0.4 V1 prime. That's not going to change much. Plus 0.28 V2 prime. Now, because I'm going to simplify this equation a little bit, I'm going to get V1 prime by itself. So this is a lot like when we did ropes and pulleys. I'm just going to get one variable by itself so that when I'm solving systems of equations, it makes it a lot easier. Although there is a lot of ways to do it. All right, so I'm going to move this 0.28 V2 prime over to the other side. And so I have 0.92 minus 0.28 V2 prime. All right, is equal to 0.4 V1 prime. Now, again, I want to get V1 prime by itself, so I'm going to divide everything by 0.4. All right, let's change colors here. Let's throw this. So to get it by itself, I'm going to divide every term by 0.4. And yeah, I'm going to need some calculator here. So let's see, take 0.92 and divide it by that. I get 2.3 minus, let's see, 0.28. Times 0.4 is 0.7. V2 prime is equal to V1 prime. Woo! All right. There is, folks, is equation number 1. All right. Now, where's the best place to put this? Equation number 2, which unfortunately is going to be even uglier. All right, because we're now dealing with kinetic energy where we're going to have 1/2 mv squared for both of these. So now we know that the kinetic energy before is equal to the kinetic energy after because it's an elastic collision. All right, so here we go. It's going to get messy here, so hold on here. All right, so kinetic energy before. So we're going to have 1/2 mv1 squared. So I'm going to have 1/2 m, which is 0.4, and our v1 squared. So I'm going to have a 2.3 squared. And again, the initial velocity of our second object, the 7 ball, I think it was, is 0, so it's got no kinetic energy. All right, now that's equal to the kinetic energy after. So again, I'm going to have 1/2 0.4, that's the mass of our first object, and its velocity after the collision is v1 prime, but we're doing kinetic energy, so it's squared. All right, plus I got 1/2 the other object, which is now moving, 0.28, or I think it is anyways, the mass, and now I got v2 prime squared. Now, the one thing I can do is every term has a 1/2 in. So I can multiply every single term by 2, and that will get rid of the 1/2. All right, so that simplifies things. All right, now, again, I'm running out of room here, but I can figure out 2.3 squared times 0.4. Let's see here. So 2.3 squared, got my calculator here, times 0.4, and I get 1.06. Let's see that. Try that again. I think I missed a button. 2.3 squared, then times 0.4. Nope, I knew I missed a button. All right, so that is 2.12. All right, then I've got 0.4 v1 prime squared. All right, plus 0.28 v2 prime squared. All right, so let's see here. I'm going to leave that one. So there's my equation. There's equation number 2. All right. So now here's what I'm going to do. Again, I've got 2 equations, 2 unknowns. I got a v2 prime and a v1 prime. Same thing in this. So I can solve by substitution or elimination. The reason I got v1 prime by itself is so I can substitute. So I'm going to sub equation number 1 into equation number 2 here. All right, so instead of a v1 prime, I'm going to have to plug that into here. It's going to be messy because there's a squared there, which is never good. All right, so here we go. Told you a little bit of a math today. So we got 2.12 equals 0.4 times v1 prime squared. Well, v1 is this thing, so I'm going to have to put this in brackets and then square it. Yikes. All right, so I got 2.3 minus 0.7 v2 prime squared. There, I did that substitution. I substitute equation 1 into number 2 here. I still got this thing left over here. Now, again, the whole point of doing substitution or elimination is now I have 1 equation, 1 unknown. It ain't pretty, but I do have that. All right, so now it's simplifying things. All right, so here we go, and I'm going to change colors here because things are getting jumbled up. All right, so I have my 2.12 equals 0.4. Now I have to square all of this, a binomial squared. Something teaching math all the time, I understand that a lot of people don't know how to do a binomial squared. But I'm going to square this term, then go 2 times this, and then square this term. That's the quick way to do it. Fortunately, if you're not good at math, that's not a good thing. So I take my 2.3 squared, and I get 5.29. All right. Then I go 2 times my negative 0.7 times the 2.3. And I can't forget I have a v2 prime here too. So that's negative 3.22 v2 prime All right, and then the last thing is I got to square this term. So I got my 0.7 squared, 0.7 v2 prime squared. So I got positive 0.49 v2 prime squared. And I can't forget this last term I got over there that I don't have really room for, but I'm going to throw it down here. 0.28 v2 prime squared. Woo! All right, now I got a rainbow rule here. It's getting simpler. I know it doesn't look like it, but it is. Rainbow rule here. I'm going to take this 0.4 and multiply it out here. All right, so I got my 2.12 equals 0.4 times that. All right, so then we can collect like terms, and then we finally get going here. 0.4 times 5.29. I got 2.12. No way. All right, that's good. All right, then I got 0.4 times this negative 3.22 v2 prime. And I get negative 1.29 v2 prime. All right, now I got to go 0.4 times that 0.49 v2 prime squared. How's that for notation? 0.4 times 0.49. All right, we get basically 0.2 v2 prime squared. And then, of course, I have that term, the positive 0.28 v2 prime squared. All right. Now, this is kind of good for us. I'm going to move this 2.12 over to the other side. When I move it, it becomes negative. So 2.12 minus 2.12, there's going to be a 0 over here. Right on. All right. Now I have a v2 prime and I have a 2 v2 prime squared. So I'm going to put these two guys together. So I'm going to have a negative 1.29 v2 prime plus these two guys I put together, and I get a plus 0.48 v2 prime squared. All right. Now, here's the key here. This is a quadratic equation to solve because I want to find v2 prime, but I have a squared term and I have a regular term. But I don't have a third term here. I don't have a number. So a quick way to do this, and this is we actually had this before, is I'm going to factor out a v2 prime. And so now I have negative 1.29 here plus 0.48 v2 prime. So I factored out a v2 prime. And the reason I did that is because now I factored it, solved by factoring. You can do a quadratic equation or you can solve by factor. In this case, because I had a 0 over here and I didn't have a third term, I was able to factor a lot easier, which case you make each piece equal to 0 because there's two pieces. One's a real simple piece here. v2 prime equals 0. What does that mean? Well, we'll get to that. Let's find another because we're getting two answers, but there's only one collision here, right? All right, so we'll get to this. We got the negative 1.29 plus 0.48 v2 prime equals 0. They both have to equal 0. I'm going to move that negative 1.29 over to the other side, then divide by 0.48. All right, and I get my other answer, v2 prime is equal to, let's see here, end up with 2.67 meters per second. All right, so again, there's only one collision. How can I get two answers? v2 prime equals 0. This is saying they never hit. Kind of be like me playing pool. Miss, right? But this is what we're looking at because we know they collided, that the velocity of our white ball or our 7 ball is 2.67 meters per second. But we wanted both of them, right? Well, look at this. I have two equations to use to find v1 prime. This one's messy. Look at all the squares and stuff in there. And look at this one. We got v1 prime equals the 2.3 minus 0.7 v2 prime. So I'm going to substitute into that equation. All right, so I got 2.3. Glad I left a space here. I didn't do that on purpose. It'd be nice if I did, but I didn't. And I now know that v2 prime is the 2.67 That equals our V1 prime. And I do a little math here. Let's see here. I get 2.3. I got to multiply these first. So I multiply those, then add 2.3, and I get my velocity of my white ball after the collision to be 0.43 meters per second. I know, for those of you who don't like some math, there's a little bit of solving equations for you. The fact that there's some squareds in that second equation, what's going to happen, because we have a kinetic energy which has the V's are squared, that's going to happen. But because, again, it was an elastic collision where kinetic energy is conserved, no energy is lost. Somebody asked you, I know you at least you're not mushy. You just lost brain cells. So I guess that's just part of the brain, not the whole thing. I'm not sure. But that is, again, the difference between elastic collisions and inelastic